Welcome to this lecture on two-person zero-sum games. Imagine you and a friend find $100 bill on the ground and decide to play a game to see who gets how much of it. If you win $60, your friend is left with exactly 40. Every single dollar you gain is a dollar your friend loses. The total amount of money never grows or shrinks, it just shifts between the two of you. Today, we are going to explore the fascinating mathematics behind these situations of pure competition, where cooperation does not help and one person's victory is entirely built on the other person's defeat. Now that we have a basic intuition, let us define this formally. In game theory, a two-person zero-sum game is a mathematical model representing a conflict between exactly two rational decision makers. We call them players. The term zero-sum means that the mathematical sum of the players' payoffs is always exactly zero for every possible outcome. Whatever player A wins, player B must lose, and vice versa. We typically represent this game using a rectangular grid of numbers called a payoff matrix. By convention, the numbers inside this matrix represent the winnings for the row player, usually player A, and the losses for the column player, usually player B. Both players are perfectly rational. Player A always tries to maximize their own payoff, while player B always tries to minimize player A's payoff to protect themselves. Understanding how these rational players think leads us to two fundamental concepts. Player A knows that player B is smart and will always try to minimize player A's gains. Therefore, player A looks at the worst possible outcome for each of their own strategies, which corresponds to the minimum number in each row. Player A then chooses the strategy that provides the best of these worst outcomes. This is known as the maximum of the minimums, or the maximin strategy. Conversely, player B looks at the worst possible outcome for each of their strategies, which is the maximum number in each column. Player B then chooses the strategy that provides the best of these worst outcomes, known as the minimum of the maximums, or the minimax strategy. This logical deduction brings us to our first mathematical formula. This formula mathematically represents player A's conservative strategy. The symbol Aij represents the specific payoff when player A chooses row I and player B chooses column J. The inner part of the formula finds the absolute lowest payoff in a specific row, representing player A's worst case scenario for that choice. The outer part then looks at all those worst case scenarios and selects the highest value among them. If the payoffs in a row increase, the minimum might change, potentially altering player A's final choice. This ensures player A gets the best possible result even when player B plays perfectly. Now that we have seen player A's perspective, let us look at the formula for player B. This formula mathematically represents player B's defensive strategy. The inner part of the expression scans a specific column to find the highest number, which represents the maximum amount player B could possibly lose if they choose that column. The outer part then compares all of these maximum potential losses across every column. It selects the smallest value among them, ensuring player B minimizes their maximum possible loss. If a column's maximum value decreases, player B is more likely to choose it. This guarantees player B the safest possible outcome against a rational opponent. Having defined both strategies, we can now combine them to find a stable solution. This equation is the ultimate test for stability in a two-person zero-sum game. It checks whether player A's best conservative strategy perfectly matches player B's best defensive strategy. When these two values are exactly equal, the game is said to have a saddle point. A saddle point is a highly stable outcome when neither player can improve their position by changing their mind. The matching value is denoted by V, which stands for the value of the game. If both players are rational, they will naturally gravitate to this saddle point, and neither will have any reason to change their strategy. Before we move on to a full calculation, let us see this visually. The diagram on screen demonstrates how a saddle point is found in a payoff matrix. You are looking at a grid where player A's strategies form the rows and player B's strategies form the columns. By listing the minimums of each row on the right and the maximums of each column on the bottom, we can easily compare the maximin and minimax values. Notice the blue circle highlighting the highest row minimum and the red circle highlighting the lowest column maximum. When the highest number in the blue circle matches the lowest number in the red circle, that specific cell in the matrix becomes the stable solution for the entire game. Now that we have seen the visual representation, let us solve this example step by step. We are given a game with two players, A and B, each with three possible strategies. We need to find the optimal strategy for both players and determine the final value of the game. We will do this by finding the worst-case scenarios for both players. First, we evaluate player A's strategies by finding the minimum value in each row. For the first row, the payoffs are 3, 2, and 4, so the minimum is 2. For the second row, the smallest number is 4. For the third row, the absolute worst outcome is 0. These are the guaranteed minimums for player A. Continuing with our analysis, player A must make a rational decision based on these worst-case scenarios. Player A wants to maximize their payoff, so they will choose the largest of the minimum values we just found. The maximum of 2, 4, and 0 is 4, which becomes our maximin value. Now we switch our perspective to player B, who wants to minimize the payoff given to player A. We look at the maximum possible losses in each column. For column 1, the worst case scenario is 4. For column 2, the maximum value is 5. And for column 3, the highest number is 9, which is a terrible outcome for player B. With all worst-case scenarios identified, we can now find the final solution. Player B must choose the safest strategy among their maximum possible losses. To protect themselves, player B will choose the smallest of these maximum values. The minimum of 4, 5, and 9 is 4, which is our minimax value. We now compare the maximin value and the minimax value to see if they match. Both values are exactly 4, which means the game has a stable saddle point. Neither player has any reason to deviate from their chosen strategy. The value of the game is 4, meaning player A will consistently win 4 units and player B will consistently lose 4 units. This perfect stability we just found leads us to an important question. What happens when the values do not match? Not all games have a stable saddle point. In highly competitive scenarios, if a player relies on a single predictable strategy, their opponent will quickly figure it out and exploit it. To prevent this, players must use a mixed strategy. A mixed strategy means a player randomizes their choices using specific probabilities. By doing this, they make their opponent completely indifferent to their own choices, ensuring the best possible average outcome over time. Before we calculate probabilities, let us see this with a concrete example. Consider a simple coin matching game between two players. Both players secretly choose to show either heads or tails. If the coins match, player A wins 1 unit. If they do not match, player B wins 1 unit, meaning player A's payoff is -1. First, we check if this game has a saddle point. For player A, the minimum of both rows is -1, making the maximum value -1. For player B, the maximum of both columns is +1, making the minimax value +1. Because -1 does not equal +1, there is no saddle point. Since there is no saddle point, we must use algebra to find the optimal mix strategy. Let us assign a probability P to player A choosing heads, which means the probability of choosing tails must be 1 minus P. If player B decides to play heads, player A will win 1 with probability P and lose 1 with probability 1 minus P. We calculate the expected payoff E1 by multiplying the outcomes by their probabilities, giving us 2p minus 1. If player B plays tails instead, player A loses 1 with probability p and wins 1 with probability 1 minus p. This gives us a second expected payoff, E2 equal to 1 minus 2p. Now that we have our expected payoff equations, we can solve for the perfect probability. A perfectly optimal mix strategy means player A's expected payoff should be exactly the same, regardless of what player B chooses to do. Therefore, we set the expected payoff from player B playing heads equal to the expected payoff from player B playing tails. This creates the simple linear equation. 2p minus 1 equals 1 minus 2p. By adding 2p to both sides and adding 1 to both sides, we get 4p equals 2. Dividing by 4 gives us p equals 0.5. This means player A should flip a fair coin, guaranteeing an expected game value of exactly 0. Now that we have solved these games mathematically, let us understand why this matters in the real world. Two-person zero-sum games are the foundation of strategic decision-making in highly competitive environments. In business, they model scenarios like two companies fighting for a fixed market share, where every customer gained by company A is a customer lost by company B. In computer science, these exact algorithms are used to program artificial intelligence for board games like chess and checkers. Ultimately, understanding these games teaches us how to minimize our maximum possible losses, which is a crucial risk management skill in finance, military operations, and daily life. We have covered a lot of ground today, so let us review the most important ideas. First, a two-person zero-sum game represents pure competition, where one player's gain is exactly the other's loss. Second, we solve these games by looking for a saddle point, where the maximin equals the minimax, representing a stable, conservative strategy for both sides. Finally, if no saddle point exists, players must use mixed strategies, randomizing their actions to remain unpredictable and secure the best possible average outcome. You now have a solid mathematical foundation for analyzing competitive strategies.